Hey everybody. All right, so this video we're going to talk about what we're going to call measures of the center of data. Okay, so we'll have a few different ones of these. It's a weird phrase. Anyways, we'll have several different measures of center. Okay, let's write this. Measures of the center of data. Okay, and there are three that we're going to look at. We're going to look at the mean, the median, and the mode. Okay, and for us, we're going to use the mean and the median quite often. We will use the mode a lot less. We're just going to expose ourselves to it, practice it a little bit, but it's not going to be a big thing we're going to use this quarter. So first of all of these, though, their purpose, or one purpose, certainly, maybe their most important purpose, is they want to try to capture what do we mean by the typical piece of data. Okay. Now, this is not a very precise phrase, and it's not necessarily something we can come up with a precise phrase for. What do we mean by typical, right? And we'll see the differences that can come about in the meaning of these. But in this video, I mostly just want to define these things, and we'll have another video where we kind of talk about the differences of when we will want to use one over the other. Okay, so let's start with the mean. Okay, technically speaking, this is called the arithmetic mean, but it's the only mean we're going to talk about, so we're just going to use mean. There are other means out there. There's something called the geometric mean, and there's others as well. But for us, we're gonna just talk about the mean. In common language, people will say average to mean the mean. Technically, that's not really the precise definition in statistics. I'm going to allow it because it's so common. So we'll use average and mean mostly interchangeably, but in a most technical sense, average is just another word for a measure of center. And in a lot of books, all of these would be called averages. They're just different kinds of averages. So the mean is probably the one most of us are most familiar with. The mean is just the sum of data values divided by the number of data values. Okay. In other words, you add up each one of your data values. So sometimes we might use something like x1 plus x2 plus each of these x's represents a data value to the nth, right? That's the first data value, the second data value, the third, and on and on and on up till the nth if we're dealing with n data values. Right? And we also have a shorthand for this when we're adding something up over and over and over again. This strange Greek letter just means add up all of these things. So I'm using x sub I to represent x sub 1, then x sub 2, x sub 3. You don't need to master this notation. I will use it on occasion, but I will be reminding us of what it means each time. So it's not going to be an issue, but it's a nice handy notation. And as you move forward in science and start reading papers, this notation called summation notation is used everywhere. Okay, so we will eventually have to get a bit used to it, but we won't do a huge amount with it here. It turns out down the line that depending on if we're looking at sample data or population data, so I'll just remind us of the difference. A sample is a subset of the population. The population is who it is we're interested in studying. The sample is who we end up studying, usually because of constraints of time and or money. So for example, if I wanted to know the mean number of hours students at South Seattle College study each night, that's the population, all of the students at our school. I might sample you guys, right? So the 30 or so people in this class would be my sample, okay? So depending on whether you're looking at a sample or a population, nothing changes about how we find the mean, but we do use two different symbols because later we do different things with these things. So we have to start keeping them straight. So I'm going to introduce these now. When we're dealing with a sample, we will often use the symbol X bar, right? So it's a little X with a bar over it, but nothing changes. The formula is exactly the same. How many pieces of data are in your sample? You add up all the data in your sample and divide by how many pieces of data you have. Okay, so all I'm changing is the symbol. For a population mean, we use another Greek letter. This is the ancient Greek letter sigma. We use what's called mu. It looks like a U with a kind of long tail there. It's actually, I'm assuming, more related to an M. It's called mu, MU. And again, I'm not changing the formula. Nothing changes about how we compute a mean. I'm just changing the symbol we use for it. This won't be a big deal right now, but we are going to have to tell these apart in the future. There are things that we can do with one that we do something different with the other, and we're often using them both in the same problem. We're going to have to keep track of which one we're talking about. Okay, so let's just do a quick example of computing a mean. So for instance, suppose I have the data. We'll just make a small, simple data set. Right, so I've got 2, 3, 4, 5, 6, 7, 8 pieces of data here. Let's pretend this is a sample from something, and I want to compute the sample mean. I'm adding up all the data. And dividing by how many data we have, right? So what do we have? 3, 5, 9, 24, 32 divided by 8 gives me an average of 4, right? So a mean of 4, remember what I said, a typical piece of data, right? What is the typical piece of data in this set, right? According to this computation, it's 4. How well you think that captures the data is a matter of opinion, but this is one way that we think of to capture the data, capture this idea, a typical piece of data. I want to point something else out here. I'm just going to go back to this computation. I can do this computation slightly differently. I have 1. I have 2 plus 2, right? Or 2 times 2 plus 4 plus, I have 3 5s here, so I can do 3 times 5 plus 8. Right. Nothing's going to change, right? I'm adding up the exact same numbers. This will still work out to 4. However, one thing we might notice, this is the frequency of the data 2 times the data value. The frequency of the data value 1 is 1, so 1 times 1. The frequency of the data value 2 is 2. The frequency of the data value 4 is 1, so 1 times 4. 3, the frequency of 5 times 5 plus 8. In other words, an alternative way to calculate the mean is to take the frequency times the data value divided by the number of data. Okay, this is nice if instead of a list of data values, you have a frequency table. It's a much simpler computation, right? And certainly when I'm programming things, when I have data that I've input into a spreadsheet or something like that, I might use this as part of some other computations. This is a nice way to be able to look at it, okay? Okay, so that is our mean. Let's take a look at a couple more examples. Let me share a spreadsheet with you here. we'll get to one more idea with this. Okay, so I've created a spreadsheet here. I think I'm just gonna display half of it right now. Give me 1 second. Oops, it has disappeared on me. There we go. Okay, so here, for example, I've generated some data. So this column A is some random data between 40 and 45. I created a spreadsheet. This is a spreadsheet where each data value gets its own class because there's so few data values. I have computed the frequency of each of these. And here I did what we just said, the data value times the frequency. So I took the data value 40 times 2, gives me 80, and I get these, I multiplied all of them together, only to show you that here, this value 42.4, I've added up these data values times the frequencies to get 848, and then divided it by how many data values there are, 20, to get the average of 42.4, which is exactly the same average you get by just adding up these numbers and dividing by how many there are. So just demonstrating that that still works here. The real reason I like that method, though, it's not really much simpler to multiply each data value times its frequency and then add them all up, right? Especially in a computer, I can just ask the computer to compute an average of a list of numbers just as quickly as programming that. But here's why we really care about that. Let's look at this. Let's zoom in a little bit on this. Let's look at this frequency table over here, okay? So I've got the data here, but I'm gonna move it off screen. So all we're seeing is, I hope this is all we're seeing, is this frequency table, right? This is a, oh, this is actually, let me relabel this. I copied and pasted. This should be our upper limit for each class of data. So this category here, this class is from 100 to 110. This is from 110 to 120, 120 to 130, and on and on and on. So I have data now that goes from 100 up to 200, okay? And I've created a frequency table for those data, all right? So there are 13 values between 100 and 110. There are 9 values between 110 and 120, 7 between 120 and 130, and so on, okay? So if this was all we had, if we didn't have the actual data in front of us, we had maybe somebody's report on data, we might still want to estimate the average, the mean, okay? Well, what we did last time was we multiplied a data value times its frequency, okay? But I don't have data values now, I have ranges of data values. There are 10 possible, or I guess 11 in this particular category, from 100 to 110 is 11 possible data values. These 13 pieces of data could be any of them. They could all be 100, they could be 100, 101, 102, and then 103 10 times in a row, right? Or any combination therein, right? So we don't know what these 13 data values look like. But here's what we can do. We can approximate what they look like by pretending each of them is the midpoint of this class. This class goes from 100 to 110, including both 100 and 110. So the midpoint is 105. So that's what I've done with this number. I multiplied 13 times 105. This one's a little bit different. I don't want to get bogged down in the technicalities. I'm still multiplying the midpoint by the frequency. The midpoint for this one, this class only includes, this class goes from 110 to 120, but it doesn't include 110. So there's actually fewer numbers. Now the midpoint is 115.5 instead of 105. But still same idea. I multiplied the midpoint times the frequency to get this number. So every number in this column is the midpoint of the class times the frequency of that class, okay? And then I added them all up right here to get this 15,000 plus number. And then I divided by the 100 data values. So this square that I'm on right now, this is an estimate of the mean made by using the midpoints of each class to represent every piece of data in the class, okay? So it's a nice, simple way we can estimate that data. Well, I actually have this data, so I don't have to estimate it. I just wanted to show you what an estimate could do. Here's the estimate of the actual data, where I'm not estimating as midpoints. Sorry, here's the mean of the actual data, where I'm not estimating using the midpoints. I just added up all the data and divided by 100. Notice how close these are. My estimate is 151.635. The actual mean is 151.9. So we're off less than 3/10 of a unit, right? Which is pretty good for data that's this size, okay? So that's a nice estimation, and a nice formula to estimate data when you don't have the actual, data. You can multiply by the midpoint, okay? All right, let's take a look at our other measures of center. So let me go back to my paper. So the next one is the median, which we've already seen. The median is the same as the second quartile, as Q2, right? So the median is, let's just say, the middle data value. But we have to be a little careful. This is kind of an imprecise sentence. I'm just going to illustrate what I mean precisely by an example. If here's my data, sorry, I need to put it in order. Sorry, it's got to be the middle data value when the data is listed in order. Pardon me. So let me try this again. Okay, so here are 7 pieces of data. The middle number is just this number 9, right? There's 3 numbers above and 3 numbers below. So that's the middle, okay? Let's look at the similar list of data, except we'll add one. Now we have 8 pieces of data. There is no middle number, right? Here I could split it with 3 above, 3 below, but because there's an even number of data, I can't do that. What I do instead is I split the data. Notice there's 4 above and 4 below, and I take the average, the mean of these 2 pieces of data. So 9 plus 13 divided by 2 equals 11. And this will be my median. Okay. So it's the middle number with this little extra idea that if we are dealing with an even number of data, we have to take the average, the mean of we have to take the mean of the middle 2 values, okay? So there's a simple formula for finding the middle number, right? Okay, the number of data plus 1 divided by 2. The idea is if this is a whole number, if the result is a whole number, that is the middle of the data. If the result is a decimal, take the mean of data above and below that value. So again, let me use these examples to illustrate exactly what I mean by this. In the first case, n plus 1, there were 1, 2, 3, 4, 5, 6, 7 data. 7 plus 1 over 2 equals 4. The median was the fourth piece of data. Here, where we had 8 plus 1 over 2, 4.5, the median was the mean of the fourth and fifth data, the whole number fourth and a fifth above and below 4.5. Okay, so that's what the median is for us. It picks the number, or the closest idea to the number in the middle. Okay. All right, and then one more definition. This is a really simple one. The mode is the most common data value. Okay. So if I have a list of data, so I'll just write it again. So for instance, from this previous list of data, the mode is 4. 4 appears twice, everything else appears just once. Okay. The mode is not something we're going to typically use. For instance, remember the mode, all of our measures of center are supposed to give us an idea of a typical piece of data. Suppose I had this data. Let's make it even more extreme. Okay. This might be a list of exam scores in a class, right, where 3 people didn't show up. Okay. So mode is 0, but in no way does this seem to capture the typical piece of data, right? It's not typical in this class to get a 0. If we took the average of all these numbers, we'd end up here. If we took the median of all these numbers, we'd do a lot better up here. But the mode is really useless in a case like this. The mode is almost only going to be used for us when we're talking about qualitative data, right? One thing to notice is the mean and the median can only be used with numbers. If I ask you all a survey for your favorite brand of coffee, I can't take the average of coffee brands, right? I can't add them together and divide, or I can't list them in a meaningful order and pick the one in the middle. The mode, though, we can do that. We can look at all the coffee brands and say, this many people, this is the most common answer. Starbucks was the most common, and so that's our mode. That's our most typical answer, okay? One more thing. Let's go back to that spreadsheet. And we'll talk in a little more detail about this in a little bit, but I do just want to take a moment to compare the mean, median, and mode. So here's from this data. Again, these are just random data sets that I generated. This data has a mean of 42, median of, 42.4, a median of 42, and a mode of 41. Let's look over here. We have a mean of 151.9, a median of 155, and a mode of 104. So here's a good example where the mode doesn't really tell us anything about the center, right? In this data set, 41 is pretty close to 42. It just happened to be similar to the mean and the median. But here you can see it really has nothing to do with how common this number is. There's a bunch of 104s, but we see it's way different than a lot of this data, right? This data goes all the way up to 200, and 104 is quite low. The mean and the median are pretty close in both cases, right? So we're not going to go into a ton of detail right now, but one thing that we'll use the mean a ton for some, let's say, theoretical ideas. It turns out to be a very useful number for a lot of computations, and there's lots of what we'll call distributions that we want to know it for. It does have a big weakness, though, and the weakness is it reacts very poorly to what we call outliers, right? We talked a little bit about outliers in a previous video. These are pieces of data that are very different than the rest, okay? They're very, very different than the rest of the data, and sometimes it's data we shouldn't even count, right? In that example I gave a moment ago about 3 students who got zeros, maybe they, I mean, nobody's ever shown up for a final and gotten a zero. The zeros are just people who've decided not to take it, right? People who've decided to drop the class or something like that. Should I even count those numbers in the average? I probably shouldn't, right? So outliers, it's a tricky subject, but they can often, from what we call, skew our data. Well, the mean reacts to outliers a lot more strongly than the median does. For instance, I'm going to add an outlier to this data. So here's my list of data, right? I'm going to take this number 100. Remember, this data is all between 100 and 200. And I'm going to change it to, I'll just add a couple zeros and change it to 10,000. I'll make it very different than everything else, okay? And let's look at the mean and the median and see how they change. So remember, the mean was 151.9 and the median was 155. When I change this data value 100 into something much bigger, my median barely changed. It went up from 155 to 155.5. But the average went from 151.9 to 1,150.9, right? A massive change in the average from one piece of data, right? If we're thinking of the mean as the typical piece of data, does 1,150 seem typical anymore? We do have this one huge value, but we have all of these values between 100 and 200, and now this mean is wildly different than all of them. So we can make arguments about that, but that's one of the strengths of the median, is it doesn't react to outliers very strongly. I'm going to make another video on that topic and a few other things a little later. So that's it for now. Thanks, everybody.